Somebody, it was a long time ago, right? And somebody looked at this kind of structure and invented a new one, new circuit. Which is called Nauta cell. This is a name of a person, Bram Nauta. I think he is from Netherlands, the Netherlands. So in 1992, he invented a differential amplifier using inverters. See, if you look at this one, let's see. I have one inverter here. This is connected to positive input node. I have another inverter there connected to negative input node. And then, see, I have one inverter. You can see this inverter is connected to there, right? Like that. Because, see, this input is connected there, output is connected to there, right? And then if you see this inverter is only connected to there, right? So if you see, how about this thing? This inverter is, inverter is only this thing connected there. Okay. This inverter is just connected there, right? So he invented a differential amplifier using inverters only. This is input. VIP, VIM input, VIP, VIM is connected to a logic threshold voltage of inverter, right? DC VC is a logic threshold voltage. So let's just see. That Nauta cell is in a simplified circuit. See, I have something like that. I may have this large inverter. And then you can see, you already saw this kind of circuit in chin cell, right? Cross-coupled inverter. Here see I have some inverter connected here for the logic threshold. Here I have another inverter there connected there, okay? This should be VOM, VOP. So, will it be a differential amplifier? Yes, it can work as a differential amplifier. This resistance is only 1 over GM. Okay, there is another 1 over GM here. Or maybe some arrow there, right? Parallel, some arrow, right? Some arrow. This small signal resistance of this thing is, let's see, 1 arrow. Is this 1 arrow? Twice arrow. This is twice. This is twice. Something like that. Is this 2 arrow? I think so. This is negative feed. I mean, there is a negative small signal resistance. See, what is this thing for? For simplicity, this is a GM over 2 parallel 2 arrow. This is the resistance, right? Resistance between this node and that node. Okay, there is if this thing is n times larger than this one, for simplicity, then this resistance should be Rho over n. Rho over n. Small r over n. Okay. If you neglect Rho, assume Rho equal infinite, let's just see. Yeah. Okay, don't assume that. So this one is, let's just see, say, this is a half of VID minus half of VID. Then, current flows out, right? Current flows out. This is NGM half of VID, and current flows in. The same current flows in, right? And then what's the arrow here? Yeah, my differential output, BOM over, is this a BOM? Yeah, should be. How come this is positive? Oh, sorry, wrong polarity. This should goes in, oops. This should goes in, goes out, the other way around because of inverter, okay? So BOM minus BOP should be this current, NGM half VID times that resistance, right? So those resistance will be just twice this one, twice RO over N parallel. Yeah, this thing is twice, this twice. This GM plus 1 over RO, that's twice. And then this thing, this is 1 over this one, minus GM over 2 plus 2 RO. Yeah, this should be the differential output voltage. Should be some negative sign, right? Negative sign. Yeah, if I assume this arrow is pretty large, this is infinite, okay? Because this GM and minus GM, they cancel each other, so it will increase the small signal voltage gain. Question? No. Okay, let's try to simulate this Nauta cell.
인풋을 인버터에 인풋으로 주면 인풋이 보통 조금만 변해야 동작하는
Let's see. Your question is about the input of this inverter. So can you say again?
그러니까 인풋 웨이트가 작아야만
Yeah. I think you are right. See, this one must be connected. See, I will put it something like that. Capacitor coupling, okay? So the DC operating point of input node is at the logic threshold voltage. So I will apply some small signal through capacitor. But it has a pretty wide operating range, not very small. Okay, you will see in the simulator. Okay. Yeah, we assume mostly all the transistors work in a saturation region, right? So difference of this Nauta cell from Chin cell is this is just a simple inverter. He used just a simple inverter. Okay. For all those things, there is no source follower. Okay. Okay, where is my Nauta cell? Oh, let's see. Let's look at the DC coupling first. Oh, I may have a netlist. Okay, I always forget. Oh yeah, here's my netlist of Nauta cell. What is this thing? Yeah, inverter, simple inverter, all the same. 1 by 1, NMOS, 3 by 1, PMOS. Yeah, that's a sub-circuit inverter. Yeah, I have a sub-circuit inverter, 1 by 1, 3 by 1. And inverter 10, yeah, multiplied by 10. That thing is multiplied by 10 times. So I have a large inverter, huge inverter, inverter 10. This is only IMB cell circuit. This thing is 10 by 1, 30 by 1. Okay. What's inverter X? This inverter X is some mismatched one. Some inverter X is mismatch. 1 by 1.5, 3 by 1. This is inverter X. Right? It's mismatched like 50%. Okay. Then let's construct a Nauta cell. My Nauta cell is, this I1 is input, I2 is just inverted. I will sweep this I1 node from 0 to 3.3. And how about this I2? I connect this same thing here, CDD, VDD, which is the same VIP there. This is my I2, right? So if my VIP sweeps from 0 to 3.3 volt, this I2 will change from 3.3 volt to 0, right? In the opposite way as I1, okay? So let's just see. I have two huge inverters, I1, O1. My input is I1, O1, right? I1 is my input. This is inverter 10. I2 is my input, which is I2, right? So where is this thing for? There is small inverter O1, O1, DD. Oh yeah, this is O1. Yeah, O1. No, this is it. Yeah, this is that thing. This is that thing. Okay, that's X4. How about the X5? Oh, X5 is inverter X. This is, this thing is inverter X. Yeah, mismatched thing. This is IMV. Okay. Yeah, simple. That's it. Okay. Oh, actually, I can control. There is some controller that's connected to this one. Yeah, those two supply voltages connected to some different supply. All others are connected to normal supply. VDD 3.3. VDD, okay. So this is a 3.3. If I increase this one into something else, 3.7, so my minus GM thing will increase, right? Minus GM thing will increase. So it will compensate for this 1 over GM and as well as those arrows, okay? So usually I want to adjust this VDD2 to make dot arrow to be infinite, okay? Then I can get the maximum voltage gain, okay? So, yeah, then see, this is just, do I have a DC? Oh yeah, I have some transient. Let's just start with the DC first. Yeah, where is my netlist? Do I have it here? Oh yeah, I have it here. Let's just start with something normal one. So this inverter X is a mismatch one, right? So I just use normal one, not mismatch one. So I want to use 3.3 instead of that one. I will try DC analysis. And then instead of transient analysis, yeah, I will do both, okay? So this is normal one, normal situation. Okay, let's look at the DC first. Where is my DC? Oh yeah, this is DC. So for the DC, this is my input 1, this is my input 2, and this is my output 1, this is my output 2. Oh, my voltage gain is not great, right? Those are output voltages. But you can see this slope is not sharp, right? So let's try to make a voltage gain larger. Oh, do I have a transient analysis here? Oh, let's look at transient also. Where is my transient one? Oh yeah, this is a tran. So what is my input? Oh yeah, I have a sinusoidal input with a peak-to-peak swing of 100 millivolt, right? Yeah, this is my input. What's my output? Yeah, larger one is my output, or different common mode, right? So I can see some distortion, right? My sine wave looks very distorted because too large gain. Oh, my sine wave is no good because too large gain, I have a large distortion. Okay, let's increase the voltage gain. I want to even increase the voltage gain. Let's see. How can I increase? Yeah, this one is I will say this one is 3, instead of 3.3, I want to make 4.3. Then I will have a large magnitude minus GM there. Okay, let's just see. Is it working? Fine. Oh yeah, it worked. So then this is a DC. Where is my output? Well, I saw much sharper output there, right? My gain will be very large. Okay, here, almost looks like infinite. Wow, this is infinite gain. My transient will be okay or not? It will be much larger distortion, right? Let's just see. My transient will be, yeah, input will be same. Oh, yeah, much larger distortion, right? My input will be pretty small. The same input, peak to peak 100 millivolt, and then I will have a much larger distortion here, right? Wow, there's too much distortion. If I reduce this transient input voltage like 10 millivolt, what happens? Where is my input? Yeah, here. This is 50 millivolt amplitude. Okay, I want to change it 10 times smaller, 5 millivolt amplitude. Okay. So let's look at the transient. Transient one is, yeah. Wow, this time even weird, right? Even larger distortion. How come? Much larger distortion. Looks like I reduced the GM too much. So I will, instead of 4.3, I will just say 3.5. Then what happens? Let's look at the transient. What happens? Okay, where is my input thing there? Yeah, here. O1, O2. Wow, looks fine. So if I reduce the gain, I have a very small gain, but pretty large. My distortion disappeared, almost disappeared, right? It's a pretty clean sine wave. Okay. I think some output voltage changes a little bit, right? See, this is I think this is the logic threshold. Is it right? Oh no, this is 1.65. Yeah, my output common mode level changed. It's different from input common mode. So, I can increase output resistance by increasing this supply voltage of a cross-coupled inverter. If I increase this one even larger, 3.8, then I will have a much sharper characteristic, larger gain, right? So I will just make a 3.5. Okay, let's make this distort. Let's distort one. Let's see. Yeah, we have seen it. Yeah, let me distort one side of yeah, this one. Just one of this. I just distorted this instead of channel length of 1 micron, it's 1.5 micron, 50% distortion, huge distortion, right? Only one side. What happens? Let's look at the transient one. Simulate mismatch. Say transient, say O1, O2. Ooh, yeah, with the distortion, my common mode is separated, right? So that distortion is no good. I mean, mismatch. So I cannot control my common mode, right? So let's see. If I have a same distortion here, see, this is a cross-coupled inverter. I have a same one. You know, those two cross-coupled inverters maintain the common mode output. Okay. So same thing. What happens? Same mismatch. Oh, looks fine. Good. If they match each other, the cross-coupled inverter, it works fine, right? Question.
근데 VD2 그 크로스필드 인버터의 마이너스 GM이 원래 플러스 GM을 캔슬해줘서 이제 게인이 같이 크게 나오는 건데 이게 VD2를 0.3보다 키우면은 이게 게인이 더 증가하는 이유가 뭐?
Okay. So the question is, see, if I increase this voltage, this is the voltage of those cross-coupled inverters, then why the gain is increased? Yeah, the thing is, see, yeah, for simplicity, you know, the output resistance from here to here is just my output resistance is let's see, is it 2R? Yeah, 2R over N. This is the output resistance of this large inverter parallel, and then this one over GM. I will cancel. I mean, remove, neglect this arrow. Okay, and then the other thing is see, for this one. This is a parallel connection of GM prime, right? You know, then see, if I increase this VDD2, I increase this magnitude of this GM prime. Okay, it will cancel this part. You know, this arrow is say something like yeah, the n over 2r plus GM. Actually actually half GM. Okay, sorry, this should be two there. Half GM minus half GM prime. Okay, if they are same, I have this part left, right? If I increase the magnitude of this one, I will cancel this part. This becomes almost infinite. The denominator becomes 0. Okay, then it will increase the voltage gain. Yeah.
그 GM 프라임이 너무 커져버리면은 어떻게?
Oh yeah, actually, then it may be stable. You saw the transient waveform looks strange, right? But in a filter application, so this one is adjusted to be almost 0. I mean infinite. This arrow infinite by some feedback loop. So there is something like you know, those implementation of LC parallel circuit by using some inverters. Inverters used to implement this inductor. And then see, this is actually some LC resonator. LC resonator circuit will be implemented, and then say there is some arrow thing is involved here. So so it adjusts this VDD prime to maintain oscillation. Okay. If I have a too small arrow, it will die out. If I have a negative arrow, it will grow up, right? So by adjusting this voltage, so this state is maintained. This steady state is maintained. That state corresponds to infinite arrow. Okay. Yeah, there is some two loops. One is this arrow loop, and then the other is some PLL loop, the frequency loop. The frequency loop adjusts the GM over C. This is the inverter GM. This one is set to some frequency. See, there is some VCO, voltage controlled oscillator, and then there is a phase locked loop, and then that VCO thing is maintained to set this GM over C to some value determined by input frequency. Okay, two loops. One is a Q loop. That Q loop makes this infinite arrow.